Good morning, students. Dear students, in continuation with chapter 4, that is motion in a plane, we are proceeding towards part 14 of the video lecture. As in the previous lecture, we had discussed about numericals based on projectile motion. We had solved good numericals, two numericals we had solved, which is based on projectile motion. Now, for today's discussion, previous video we had discussed about numericals based on projectile motion, and in today's video we will discuss about, first thing we will discuss about uniform circular motion. Then after we will discuss about some terms related to uniform circular motion. Terms related to uniform circular motion. Then in this context we will discuss about time period, frequency, angular acceleration, angular displacement, angular velocity, all things we will discuss. After that we will discuss about relationship between angular velocity, frequency and time period, and then a relation between linear velocity and angular velocity. These things we will discuss in today's video. So look at the topics of today's discussion. That is the first topic, uniform circular motion. Uniform circular motion. As it is clear from the name, means in this case we will discuss about the motion which is traversing the circular path. But here we discuss only about the statics of uniform circular motion. We only discuss about the statics of uniform circular motion. We need not to discuss about the dynamics of circular motion. Dynamics of circular motion means what are the causes which makes the particle to move in a circular motion. These things we will discuss in the chapter laws of motion. After learning the laws of motion, after studying the laws of motion, we will discuss about the dynamics of the circular motion. Now here we only discuss about the statics of uniform circular motion. Means what is the path traveled, what is the angular velocity, what is the angular displacement, what is the relationship between that, all things we will discuss. So let us start the concept of uniform circular motion. What is uniform circular motion? Uniform circular motion, as it is clear from the name, any object which is making a circular path, with uniform speed. Now look at here, student. Speed is uniform means if here the particle is moving with 3 km per hour, then here also the particle will move 3 km per hour. Here also a particle will move 3 kilometer. Matlab the speed of the particle is always 3 kilometer per hour. But one thing you are noticing, that the direction is always going to be changed. The direction is changing, and since the velocity is speed is constant, but direction is changing, means velocity is changing. Velocity is changing. And if velocity is changing, because velocity depends on two things, velocity, as we had studied, velocity depends on two things: magnitude plus direction. Magnitude plus direction. Here magnitude is fixed. Magnitude is fixed for throughout motion, but direction is changing. And on the basis of this, we can say that velocity is changing. And if velocity is changing, it means to say that the body is accelerating on the circular track. Body is accelerating on the circular track. Then how we can define uniform circular motion? We can define uniform circular motion as when an object follows a circular path. When an object follows a circular path at constant speed, the motion of the object is called uniform circular motion. The motion of the object is called uniform circular motion. When object follows circular path at constant speed, the motion of the object is called as circular motion. As we had discussed before, that the speed is constant but direction is changing, so velocity of the object is changing, and as the velocity of the object is changing, so the body must be accelerated. Some examples we are discussing for uniform circular motion. Examples of uniform circular motion. Motion of tip of second hand of clock, and the second one is motion of a point on the rim of a wheel rotating uniformly. This is a clock and this is the tip, so this tip will follow a uniform circular motion. Or suppose we are taking a rim and a point is taken here, and as the rim moves, this point moves, the motion of the point is a circular motion, that is uniform circular motion. Now, certain terms related to uniform circular motion. Now, dear students, we will discuss about some terms related to circular motion, and the first term is angular displacement. Angular displacement. angular displacement. It is analogous to linear displacement. In a linear displacement, in case of linear displacement, what happens? A body travels from point A to point B on a straight line. On a straight line, and difference between the final position and initial position is called as linear displacement. But when we are talking about the angular displacement, means there is point O and the object is here, means the object is shifting a circular path. And if this is O, this is point P, this is point Q, and the object had shifted from point P to point Q, making an angle theta with O, Suppose this is delta theta, that is change in angular position. Delta theta is what? Change in angular position. This is delta theta, and this change in angular position is called as angular displacement. This change in position is called as angular displacement. This is called as angular, delta theta is called as angular displacement. Now, you know that the angles are measured in radian. So, the unit of angular displacement is radian. It is denoted by delta theta, and delta theta unit is a radian. The unit of angular displacement is radian. It is dimensionless quantity. Why it is dimensionless quantity? It is a dimensionless quantity because suppose an object here point P, here point Q, and the object shifted from to this position theta, angle theta can be given as arc upon length of arc upon radius. So since it is the ratio of two lengths, so it is a dimensionless quantity. It is vector. And direction is given by its Fleming's right hand rule. Its directions is given by right hand rule. Direction is given by right hand rule. Suppose this is your right hand, its direction is in this direction, outside the plane. Its direction, since it is moving, suppose it is moving from Q to P, then its direction will be inside. Now the second term is angular velocity. The next term is angular velocity. Angular velocity. Angular velocity. Defined as defined as time rate of change of angular position. Time rate of change of angular position. Suppose this is circular motion, an object is here and it's shifted from point P to point Q, making an angle delta theta. So whatever time, here the time plays a major role. Delta theta is the change in position, so delta theta per unit time, delta t, what is the time at point P and what is the time at point Q. The ratio is radian per second. Radian per second is its unit, and its dimensional formula is m0 L0 t minus 1. m0, it is a vector quantity. Angular velocity is a vector quantity. Now, instantaneous angular velocity. In this we will discuss instantaneous angular velocity. Instantaneous angular velocity, omega instantaneous is equal to limit delta t tends to 0 del theta upon del t, and it is equal to d theta upon dt. This is the instantaneous angular velocity, angle traced upon. So suppose an object is moving, this is point O, this is point P, this is point Q, and object is moving in this direction, then this is omega. This is omega, is the direction of angular velocity. Similarly, point P, object had moved point Q, this is angle theta. B, this is the direction of angular velocity. Now, time period, as you are knowing that time period, total time taken to complete one revolution, that is time period. These are the basic terms which are related to circular motion, so I am elaborating. You had already studied in previous classes also. Not very big things are this. Time taken by a particle to complete one revolution. Time taken by a particle to complete one revolution. It means to say that suppose this is the circular motion, this is point O and here point P, and object is traversing a circular motion, whatever the time taken by the particle to reach again to point P, this is called time period T. This is the time period T, measured in second. Measured in second. This time period is measured in second. Now frequency. Frequency, you had already studied frequency, number of oscillations per second, means in 1 second as many times the particle completes its revolution, that is the frequency of that object. Number of revolutions completed per unit of time. Frequency. Number of revolutions completed by the particle per unit time. Number of revolutions completed by per unit time, denoted by F and measured in hertz. That is, frequency is equal to 1 upon time period. Obviously, by unitary method you can also discuss. For one revolution t, for t revolutions, t is the time period for one revolution. So number of revolutions per second, it is given by 1 upon time period, and this is number of revolution per second is called as frequency. Now angular acceleration. Angular acceleration as you had discussed. Linear acceleration is nothing, it is change in linear velocity upon time. Change in linear velocity upon time is linear acceleration. Similarly, rate of change of angular velocity, angular velocity of the particle. Rate of change of angular velocity of the particle, and it is denoted by its unit is change angular velocity unit. Radian per second is for angular velocity, so radian per second upon second, and it is equal to radian per second square. It is equal to radian per second square, and its dimension is m0 L0 t minus 2. Its dimension is m0 L0 2 minus 2. It is denoted by alpha. It is denoted by alpha. And this alpha is limit delta t tends to 0 del omega upon del t, and it is equal to d omega upon dt. And relation between time period and frequency. This is instantaneous, you can say that, instantaneous acceleration, instantaneous angular acceleration, because delta t you are taking tends to 0, and if you are not taking delta t tends to 0, then the simple del omega is called as average angular acceleration. Relation between time period and frequency. Relation between time period and frequency. So we had already derived time period is equal to frequency is equal to 1 upon time period. Time period is equal to 1 upon frequency, whatever you can say. Time period is equal to 1 upon frequency. Both are correct. Now we will discuss about relation among angular velocity, frequency and time period. Relation between angular velocity that is omega, frequency f, and time period. Relation between angular velocity omega, frequency f, and time period t. So if an object completes one revolution the angle traced at its axis of circular motion is 2 pi radian. If an object completes one revolution, suppose I am taking an example, suppose this is the object and from point P it starts moving and again it comes to point P, then whatever the angle subtended at the center by this object, this is a complete angle of 2 pi. This is a complete angle of 360 degree or 2 pi radian. So if time is equal to capital T, that is time period, then theta is equal to 2 pi radian. So angular velocity omega is equal to theta upon t, and it is equal to 2 pi upon t, and we can write it as omega is equal to 2 pi f. Omega is equal to 2 pi f. So this is the relation between omega, frequency and time period. So angular velocity omega can be written as 2 pi f, means angular velocity is related with frequency with the relation 2 pi f. Now relation between linear velocity and angular velocity. Relation between linear velocity and angular velocity. Relation between linear velocity and angular velocity. The relation between linear velocity and angular velocity. So linear velocity can be denoted by v and angular velocity can be denoted by omega, as we had studied linear velocity. Now from the diagram, let it be clear. Suppose this is a circular motion and O is the point about which the object is moving. This is radius r and this is point A. T is equal to initial time t, and the object is moving with velocity v1. Now if the time is t plus delta t, if here point P and the time becomes t plus delta t, a small change in time, that is delta t, and here the object is moving with velocity v2. Here velocity is v1. Since that speed is constant but direction is changing, so velocity is changing. Here velocity is v1 and here time is t, here time is t plus delta t, and the radius is r, and the angle swept, angular displacement, angle swept or angular displacement can be denoted by delta theta. So the average angular velocity is delta theta upon delta t. This is equation number 1. But linear velocity, we are knowing about linear velocity, that is linear displacement upon delta t. This is equation 2. Now if we consider this arc as delta s, this arc as delta s, if arc AB is considered as, if arc AB is considered as delta s, then delta s can be written as r into delta theta, r into delta theta, because angle is equal to arc upon angle is equal to arc upon radius. So radius into angle is equal to arc, and this arc we had considered delta s, this arc we had considered as delta s. So delta s is equal to r into delta theta. We had considered this equation as equation number 3. So if we replace delta s by r del theta, so v is equal to delta s is equal to r del theta upon delta t. So it becomes r is equal to delta theta upon delta t, and it is equal to r omega. So we can write here, from here, v is equal to r into omega. v is equal to r into omega, and this is the relation between angular velocity and linear velocity. This is the relationship between angular velocity and linear velocity. v is equal to r omega. So dear students, that's all for today's video. Go through the video and try to understand this basic terminologies of circular motion, which helps you to understand the circular motion quite in detail and move more analytically. So first of all, develop the concept of this basic terminologies, and in the next video we will discuss about centripetal acceleration and numericals based on that circular motion. So dear students, that's all for today. Have a nice day. Have a nice day and take care. Thank you, students.